And now, next session, we have Simon, our good friend from UK, doing cool stuff with a lot of things across the years, from SMS to voice and more. So I'll let him present. And again, thank you for supporting the event all these years, every year, Simon.
Thanks, Daniel. I'm Simon Woodhead from Simwood. As Daniel said, we may gathered from the posters, we're a UK-based network operator. We do predominantly wholesale VoIP, but more recently mobile, presented in the kind of way you like to consume. So native mobile devices with SIP handoff and other protocols for the other applications. Also, as of Tuesday, I'm pleased to say I'm now director of London Internet Exchange, depending whose figures you believe, the largest member-owned internet exchange in the world. More info on us and me, if you're remotely interested. I'm going to talk about three things today, and they're kind of loosely related, but they tie together with one idea. And before I tell you what that idea is, can we just have a poll? Hands up if you program or you configure SIP software of one flavor or another. Okay, pretty much everybody. Hands up if you write code. Okay. Hands up if you have console access to a router or a layer 3 switch. Okay. More than I expected, actually. My contention is that in the next 3 to 5 years, all of you who had your hands up in the first two questions will be controlling layer 3 switches or routers in your code. And if you've just switched off because you think I'm going to talk about OpenFlow, I'm not. So first of the three things is a quick update on VoIP fraud. I've spoken at past events on various methods we have for analysing intrusions, where they come from, how they do it, etc., etc., etc. Tools used, and we put together a document 3 years ago that many of you have seen. New version of it out this year. If you connect to me on LinkedIn, it's available there in publications as well as a PDF. But we've got some at the front here. I'm not going to bore you with going through the whole thing again because not much has changed. I'm just going to tell you the key highlights. And the key highlight is if you remember the methodology, the second phase of an attack was enumerating a user. So you've identified SIP equipment, you now want a valid user on it. And in the past, that used to be done through brute force registration attempts. For various reasons, as you can see, from sort of 2013, that has dropped off a cliff. And the tools used have changed in that process. How have they changed? They're now using options. Now, this is a slightly speculative approach because it doesn't work with every user agent. Specifically, what I'm talking about is putting a to user in an options request. Some equipment will give you a 200 OK regardless. Other equipment won't, and it's actually quite popular equipment. The other benefit is people don't generally raise a log entry for an options request with an invalid user. So fail to ban, which is the go-to defense against brute force attacks, is pretty much useless in a default configuration here. So using options alone, you can be identified as a potential target and a user can be enumerated with, generally speaking, you having no log entry and no blocking whatsoever. Second thing I want to talk about is what we do, partly to detect this stuff and partly to protect our own network. Our honeypots that are responsible for a lot of the research that we've talked about before are really, really simple. We put them up in, I think it was 2010. It's a vanilla free switch install, albeit with certain things turned off, an ngrep. ngrep's chucking that into Splunk, and then we're doing SIP parsing in a really ugly way with loads of regex and things. But that's worked for years to chuck out the kind of CSVs that you've seen before, analysing source IPs, methods, etc., etc. We wanted to evolve that. and we've moved it to this. And this is an architecture that enables us to analyze this stuff network scale. So in our case, kind of nationwide, we maintain 10 data centers in 3.5 cities. Any competent equipment, be it a layer 3 switch or a router, will have the ability to mirror traffic, either as a static configuration on the port, i.e. copy all traffic on this port to another port, or in an ACL where you can do it in a slightly finer grained fashion, so copy all 50/60 traffic to this port. So in each site, next to each piece of equipment, we have a node, and that node has these span ports or mirror ports feeding into them. We're then using Kamailio. And before I show you the next slide, I'm not a good Kamailio guy. In the past, we've had several people in the room that have helped us with our own deployments of Kamailio. It's not something that I profess to be any kind of expert, so I'm going to go through them really quickly so you can't see any mistakes. But Kamailio sits there to essentially receive that traffic and to do the SIP parsing that we used to try and do in regex. And we then put them into Redis. We could have used an alternative queue engine, but we're using Redis quite heavily, so single tool, fairly disposable traffic. From Redis, they go into a couple of daemons that I'll talk about, and ultimately are archived long-term into Elasticsearch with all the legacy honeypot data that we had from before. The Kamailio piece, we're using two modules. The first is SIP capture. We have the box in promiscuous mode, using SIP capture so Kamailio can actually receive the packets that aren't necessarily destined for it, regardless of the IP address that they're destined for. And then we're using NDB Redis, just literally to chuck things in Redis. That logic really is just a whole load of guff saying, let's put this packet in Redis. The reason we've exploded it out on multiple lines was due to some sort of escaping issues, but we're taking key pseudo variables and chucking them into Redis as an event. We then have our two daemons, and the fast worker is looking at those events. Those events only actually live in Redis. I don't know if sharp-eyed of you noticed the expiry on that. They don't actually live in Redis for a few seconds. And the fast worker is trying to identify sub-second stuff. And it's written in Node.js, and all it is doing is maintaining counters for various different common fields. So for example, a counter for a common to user, a counter for a common from user, a counter for a common user agent. And for each of those counters that it's maintaining, it is also maintaining a list of IP addresses that are the source of those events contributing to that counter. And that enables us to look at effectively a league table of rate events. And in the event of any of them triggering a threshold, we've got a list of source IP addresses. That's all it's doing. But it's actually quite effective. SIP denial of service attacks, as you know, don't require a massive amount of traffic to be quite damaging, particularly if you've got a relational database on the back end. But generally speaking, they will have certain fields in common. It's not going to be completely random traffic. The slow worker is a bit more considered, again written in Node. And what that is seeking to do is identify the intent of the traffic. So it's looking at what was the to IP address. So in our case, this is seeing all traffic across the network, including IP addresses that aren't in service, including IP addresses that don't have any kind of SIP service on them whatsoever, including IP addresses that do have SIP service and get legitimate traffic, as well as obviously the honeypots. So we're putting the traffic into kind of three buckets that we call sort of honeypot, grey or white. The honeypot is obviously bad stuff. There should be no accidental traffic going to those IP addresses. The grey traffic are things that customers with fat fingers could have conceivably got wrong, but generally speaking, there shouldn't be any traffic going to them. And then there's the white traffic where we would expect SIP traffic. So we can classify each event. We can also query past behavior, both our own records and external records, IP reputation, that kind of thing. And ultimately, we can take the relevant events, because obviously we're not going to log every packet, and we can insert them into Elasticsearch. What that gives us immediately is a few outputs. And the first one is really useful in real-time voice routing to block what I've talked about in the past as test numbers. We know when equipment is successfully compromised, they don't nowadays just go straight on and dial Lithuania. They make a few calls to ordinary looking, generally geographical mobile numbers that they control. And these get lost in history because they precede when people think an attack actually started. But we know if you block them, you've effectively prevented or more likely delayed the attack because it fails the test. So we observe these in real time from the honeypot behavior. We insert them into our call routing. So essentially no customer can dial them. They change a bit, but it's generally only about 20 of them. We also get output to IP routing. Now, presently and historically, that is a source IP address that we might want to block at some level in the stack because it's full of badness. But more interestingly, looking forward, we get the 4-tuple of source IP address, target IP address, source port, destination port, which is really quite interesting because you can then start blocking stuff at the flow level without necessarily blocking all traffic from a given source. We also chuck out this. This is our portal, and this is a new threats pane that replaces the CSV files that we used to publish. This is a real-time view on Elasticsearch. You can drill down into events and query any sort of period in history that's in there. So for the IDS, that goes from December, and the old honeypot data is being imported, and it's back to, I think, October 2014 at the moment, but ultimately we'll be back to 2011. So the third thing, we've got this IP address we want to block, or we've got this flow that we want to do something with. How the hell do we do that? Now, we could give a vendor a lot of money, and we could buy a box. IPS, could buy an SBC, or we could configure something on the host in IP tables or Kamailio config. If we look at a traditional network, where you've got your core at the very center, you aggregate your access, then you have your hosts. And bear in mind, this is a single site. This could be replicated across multiple sites, potentially international in a large network. Where the hell do you put this magic box to actually be effective? You can buy lots of them, but that's going to get very expensive if you want to stick them sort of at the customer edge, and they're going to need to be very big if you need to stick them in the core. They have a place, but they don't effectively scale. I'm not saying you can't buy a firewall big enough to run through traffic on a huge network, because of course you can. But if you look at our network, where we've got something like 600 peers and 800 customers, am I going to funnel all those through a very expensive single point of failure, or am I going to spend a ridiculous amount of money to have lots of them? Neither are desirable. So the actual solution is to use the network itself to defend itself. And this is an area where networking kind of lags way behind the rest of the world, partly because network engineers are a conservative bunch, and because network vendors have historically had massive lock-in. But the ideal is to use the network to defend itself at every level, and pick and choose how deep you want to inject a rule into the stack. But fundamentally, you can block stuff on the hosts, or you can block stuff in the core, and hopefully everywhere in between. So how do you do that? Well, ACLs. You could use BGP, or to use that god-awful word that creates the same shudder in network engineers as saying SBC to a SIP guy does, you could use SDN. So an ACL, access control list, for those of you not familiar with it, they're generally applied per port. We've got some equipment in production where you can't apply a new one without removing the old one on a per port basis. You do that whilst logged into a device over a console. And they're not really feasible to change on a network-wide, yeah, you can script things with Ansible, but you're scripting something to SSH into every box and to deploy a text-based configuration to every port on that box. It just doesn't sort of scale network-wide. Obviously, they're part of the mix, but they're generally used for static config. Now, I continually internally say, we've changed our ACL once this decade, we're not doing it again. That's the level of centrality that they have. Now, yes, you can speculatively deploy an ACL on a port specifically for that port, and many networks do, but we're talking here about whole of network policy. The other option is BGP. BGP obviously scales. It runs the whole internet, and it can be very useful internally for security. This is one of our principal defense mechanisms. Now, BGP itself is a protocol for advertising prefixes, so you're really controlling the routing of the to address, not the source address. So you can black hole, and you would do this routinely if you had a DDoS against the specific host. You would say black hole traffic to that host, bin it on the edge of your network, or even upstream to protect the network from that traffic. But you're not really getting source-based filtering, which for this use case is what we're actually interested in. But there's another technology called unicast reverse path forwarding, or URPF for short. Excuse me, my mask on, horribly dry. Which essentially checks that you have a route back to where the packet came from before it allows it to be forwarded internally. And if you have set a black hole for the source address, URPF, in short, gives you source-based filtering. So BGP, pushing routes out to routers that have URPF configured on the edge ports, give you effectively source-based filtering that you can push out with a single protocol around your whole network. And as you know, BGP works to any scale. And the good thing is, BGP, standard protocol, there's brilliant tools out there like ExaBGP, where you can script the publishing or the removal of IP addresses in whatever language you choose pretty much. You can link this into real-time data and push and remove things to your heart's content, frankly. But the problem with this is it's pretty nuclear. If you block a source IP address on your edge, you're obviously blocking that for your whole network. So in our case, we're not only blocking it for the whole network internally, we're also blocking it for other ISPs that will use us for transit. So it might be appropriate in some really bad cases, but it's not the kind of thing you want to do too liberally, because it can have undesired consequences. The third option is that scary word, SDN. SDN, software-defined networking, seems really sensible to all of us here. You're separating your forwarding plane from your control plane, exactly like we do with SIP and RTP. The control plane, you're putting in software controllers, and you've got total control of the packet from layer 2 upwards. I've had an ARC request, do I respond to it? On paper, your network becomes something you can program. It's really, really cool. But it's had so much vendor hype, and vendors generally want to sell you an expensive box where you can take all of this network that you built across multiple data centers for resiliency and consolidate it down into a handful of very expensive controllers that they control and you've got very little input into. So network engineers, being a cautious breed to start with, I mean, there's some I know that are still waiting for the business case to deploy IPv6, which Ole will love to hear, haven't adopted it at all. Academic networks and some enterprise networks have jumped on the OpenFlow bandwagon, but SDN hasn't happened yet. But there's a few things coming down the line that I think might change that. The main one is merchant silicon. Hands up who knows what I'm talking about when I talk about merchant silicon. Okay. Routers and switches made by, say, Juniper, Cisco, Brocade, they all run what are called ASICs. So ASICs are custom silicon made by the manufacturer, consequently very, very expensive. More recently, you can buy what's called merchant silicon. So this is from Intel, Broadcom, some of the other chipset manufacturers are making the hardware that runs high-end network devices, but in commodity boxes. So for like £3,000 or £3,000, euros, whatever, you can buy a Supermicro box, looks like a server, but it's got 48 10 gig ports on it, and you can install Linux on it. That is merchant silicon, and the box that you can install something on is what people refer to as white boxes. So what is about to happen to people's networks is what happened to the server market, 20 odd years ago. Oops, I'll come back to that. So yeah, you can install Linux, but it's important to, or there's even distributions of Linux, like Cumulus Linux, that are specifically geared around running a network device. You can install the usual software devices like Quagga and various similar things on the box to do what you normally would, but it's important to distinguish this from things like MikroTik, where it's software routing. The routing, the packet forwarding, is happening in hardware. You've just got control of it on a box. And because it's a Linux OS, or because it's an open OS, you can install a container on it if you want to do some funky kind of packet trace or some kind of dump. They have APIs. There's one vendor that sort of sits somewhere between open source and the closed source. Cisco will call the Arista number 2 in the world now for shipping switches. They have an XMPP daemon on there. So you can check BGP status from your Apple Watch, as one of my peers demonstrated on YouTube the other week. Or you can install your own code. And that is really exciting. It's actually one of the most exciting things I've kind of had the veil lifted on in quite some time. I want to talk in a bit more depth about merchant silicon and what all this means. And if they have me, hopefully I'll do that at ClueCon. So we talked about 3 things. How fraud's gone. If you want one of those, come and see us. They're all in this bag here, and it's bloody heavy, and I don't want to carry it home. How you detect it dynamically. Hopefully there's a few ideas for you there, and how you can push that out to your network edge. But the real thing I want to leave you thinking about, because you guys are actually the future of an industry that you're not involved in yet, is that you will be programming IP networks in 3 to 5 years. Thank you.
Okay, so questions from the audience. I have one with the VoIP fraud, as usual. It's one of the revenue resources for consultants. Over all this year, because you came with some past presentation, do you see any behavior? I mean, the margin, it's kind of lowering for the minutes. Do they change and they try to penetrate or to target some specific services more than in the past, as you remember?
The key thing that has changed, like, 5 years ago, you'd know you were under an attack because stuff had stopped working. You had users registering through a database lookup, and all of a sudden your users all went offline because their registrations wouldn't be authenticated because the database was busy sort of processing lookups for sort of false attempts. Now, many of us have moved on in terms of the back-end technology anyway, but the hackers have moved on as well. They are far, and this has been a trend over sort of three years or so, they're far more calm. It used to be that you block them, they'd be back again 5 minutes later, and there's like a fury that they got to do it as quick as possible. Now they don't. These test numbers that I talk about, we've seen those preceding an attack by sort of 3-4 months. They know they've got a viable target. Actually, they spend the time in between saying, are there any more viable targets on that ISP's network? Because it's a large prefix that may have other installs of the same equipment on it. And we've seen this. And they'll wait till a quiet time on the network, like Christmas Eve is a classic, and they'll go for it. You block them, they won't necessarily come back again. They'll let you think that you've dealt with it. And if I had £1 for every time I've heard of the word, oh yeah, we must sort this out, or we must employ some of your fraud controls, These guys know that because they know they can come back 24 hours later and bugger all will have changed. But the whole thing is professionalized and got a lot calmer. And you can see that in the scanning approach. They're not tripping rate limits generally. They're not generating sort of mass sort of error or authentication failure logs, and they're sailing under the radar.
Okay. Question.
Okay, two-part question. First is, when will they get more intelligent than just looking and then brute forcing the attack?
It's a little bit like, sorry, Daniel, I've just wrecked your table. It's a little bit like a bear attack that, you know, what is it they say? You don't have to be able to outrun a bear. You just have to be able to run faster than the person next to you. And frankly, you know, as long as people are doing apt-get install and running services unprotected on UDP 5060, then why bother being any cleverer?
The second question is, where do I get those white boxes, and what would you empfehlen? Recommend?
Come to Cluecom. No, for our network, we're going, and what I want to talk about in the future is what we'll have done to a greater extent by then. We're throwing out our legacy vendor of Brocade, and we're entirely moving over to Arista. We're replacing big, heavy routers with layer 3 switches. The distinction being a compromise that you get in terms of increased port density gives you lower table size, so you have to do more in software. But if you want white boxes, I know Supermicro make them, I think Dell make them. Just search white box, or look at Cumulus Linux, which is the product that you would install on one of those, and you'll see other devices. The great thing about it is that the hardware, just like servers, has become a platform. It's now in the software and the silicon, and there's different kinds of silicon, and it has different features, so they're suitable for different applications. But it all has the same in common. You've got this massive, you know, like boxes we're buying are in a 1U chassis, 96 10 gig ports in a 1U chassis. So you've got a terabit per second of forwarding there in a box. The same vendor is making boxes up to 15 terabits per second. That historically would have cost you gazillions on, you know, vendor silicon.
Okay, thank you, Simon. Thank you for coming back and helping with the event.